Welcome, Hornets. Today we're going to be taking a look at some examples of determining convergence and divergence using our flowchart um, with p-series, arithmetic, geometric, and telescoping series. So on your screen, you'll see a couple of examples that I have in front of us, and we're just going to go through the basic concept. So if I am looking at this and I am asking myself, does 5 over 4 to the nth power for the limit as n approaches infinity go to 0? That's the first question. The answer is no, and we can stop and say that this will diverge. Notice that that's the first step, is checking for the nth term test. We always do it first. Some people might have wanted to look at that and say, hey, it's a geometric series where the common ratio is greater than 1. It must diverge. And although that's true, we never actually get to that step. We go to number 2. Notice that this is already a decomposition that's broken up into two linear terms, both of which are harmonic in nature. This will automatically converge. Now we can clearly see that the limit as n approaches infinity for 5 over n minus 2 over n plus 3 does indeed go to 0 at infinity for each and every term. Not only that, but it's telescoping. So yes, it satisfies the nth term test, and it is telescoping, and therefore we have a convergence of the series. Look at number 3. You'll notice I'm starting to get tricky now. In number 3, I have an actual sum. And because I have an arithmetic piece plus a geometric piece, I can clearly see that 1 is going to be added infinitely, which means that this has to diverge, even though the 3 over 2 n to the second power will converge. This is very apparent when we take a look at our limit as n approaches infinity. Notice this approaches 1, not 0. And because it does not approach 0, we know that the series must diverge. So you'll notice I can look at it in multiple ways, but if you do start with the nth term test first, you're going to find your life a lot easier. Let's take a look at our fourth example. This is a p-series. Notice that the p-value of n, that power of n, is greater than 1. It is not OP. We can also see that the limit as n approaches infinity for 1 over n to the fourth does indeed 0. So we have it equaling 0, and we have p is greater than 1. This is a p-series that must converge. This brings us to our last example. Now in this one, I'm trying to trick you once again because I've got that negative power of n. With the negative power of n, we want to rewrite it so that it is cleaned up and apparent. Notice this gives us now 7/12 to the nth power, and as I do my limit, as n approaches infinity, for 7/12 to the nth, I get 0. I can also see that the common ratio, r being 7/12, is less than 1 but greater than 0, and therefore it will converge. Now, what you're already starting to see here is situations where the rules can get a little confusing. For example, I'm looking at 7/12 to the power of n, which is a common ratio. And that common ratio has to be between 0 and 1. Whereas a p-series can't have a p between 0 and 1. That would make the p-series diverge. So your job is to kind of circumnavigate yourselves through the shoals and rocky waters of this flowchart. And make sure that you remember, always do the nth term test first, Then look at the series. Is it arithmetic? It will diverge. If it's geometric, look at the common ratio. If it's a p series, look at the power of p. If it's telescoping, decompose it and make sure that you are looking at two terms that are harmonic in nature, and you will then most likely have a convergence. All right. Keep in mind that the telescoping series that we will work on in this class will all converge. Okay? So you can kind of rely on that simply because I'm not going to give you something that will diverge yet. That's what we have for today, Hornets. I hope this helped clear up how we use the flowchart and how we use these rules in conjunction with each other. Thank you very much. Please be safe and take care. Have a great day, Hornets. Bye-bye.